Okay, we're on. I'd like to talk about a couple of mathematical models coming from biology, specifically from ecology, the study of populations. First, imagine that we have here a population of white-tailed deer for a dozen years, and here are the populations placed in thousands for the sake of convenience. And the values are here in the spreadsheet. So on the note packet handout, some of the graphs are already generated, but I'd like to run through that process and the whole thought process of the problem. It's a very good idea when you first get a data set to do a graph and look for patterns and abnormal things to get an idea of what lies ahead. So for paired quantitative data like this, a scatter plot is certainly appropriate. And if we generate that, we see this pattern. We could go ahead and add legends on the graph, but this is enough to show that clearly a linear pattern, for example, is not appropriate here, nor is a pure exponential growth pattern. We see growth for a while, but then tapering off. And so that's a signal that a new type of model probably would be more appropriate. So let's go back and see what we can do. We want to achieve this S-shape logistic curve kind of shape. So the characteristic is slow initial growth, then it picks up, and then levels off, and apparently levels off to something just slightly larger than 14. So let's first of all try to write a model that does exactly. Fixed points are extremely important for population models or for dynamical systems in general. They govern everything else really that happens. And so if we identify where this model should have fixed points, this is a biological model, and the species is reproducing, and so if we have nothing, no animals, no deer to start with, we never should have any. That's a strong indication that we should force 0 to be a fixed point of the model, even if that may not be apparent from the graph. That's biologically dictated. Then another fixed point from the model, as we noted, the population seems to be approaching some carrying capacity, which I'm going to say is 14.3. I don't know that exactly, but it's somewhere in that ballpark. And so now let's write a model that has these two and only these two populations as fixed points. So it's easier to think about a model for the change, which by definition is the population in year n plus 1 minus the population in year n. We want 0 to be a fixed point. The easiest way to achieve that is to be sure that whatever else is in the model, it's multiplied by a factor of Pn minus 0. And then when we plug in 0, one of the factors will be 0. The right-hand side will be 0, the change will be 0, i.e. fixed point. The other fixed point that we would like is at 14.3. Let me go ahead and do this for a moment. And now let's talk just a little bit about it. When the population is, say, 10 on the graph, what should be happening? We should continue to increase up toward 14. What will this model do? If I plug in 10, this first factor is positive, the second factor is negative, the change will be negative, and instead of increasing toward 14, I'll actually be decreasing. So that second factor isn't quite correct. We would maybe want a negative sign in front, the way it's usually written, in fact, is to switch the order of those terms and write it as 14.3 minus p sub n. Now if I have p equals 10, I have a positive factor times a negative factor is negative, and the change, a positive factor times a positive factor is positive, and the change will be positive. It's too much to expect that this equality would exactly hold. We need the flexibility of a constant of proportionality there. And that immediately then leads to the question, what would be that constant of proportionality, or what is the best choice? So we need to find k. There are two ways of doing that, at least two ways. One would be simply trial and error. Generate successive plots of what this model produces for k equals 0.5 and 3 and 0.001, and try various values and see which one matches the best. It turns out that our eye is not quite so good at seeing how closely one logistical curve follows another logistical curve. We're better at seeing trends in lines, seeing errors in lines. So let's go back to a spreadsheet and let's force a linear relationship here and do a graph. I'll go ahead and get rid of this graph for the moment. If I look at my relationship equation here, if I think about this left-hand side as being y and this right two factors as being x, then I have an equation of the form y equals kx. That should indeed be a line through the origin. And so let's generate just that. I'm going to generate a column for p times 14.3 minus p. So that's the header that tells me what's going on there, and then doing just that. This is the population times 14.3 minus the population. And let's drag this formula down. And so that will be the x's in a new graph that I'm about to make. This expression here, p sub n plus 1 minus p sub n, should be the y's. So over here, let's call it delta p. And each entry here should be the next population minus the current one. So there really isn't anything to put in the first cell. Yeah, actually there is. It's the last cell, but there won't be. So here I want this value, p sub 1 minus p sub 0. And drag that down. Okay, then here are my proposed new independent variables, my proposed new dependent variables. Let's have Excel do a scatter plot for this data. And indeed, there is a line, approximately, very, very close to a line actually. So that, at this point, since this graph is so linear, that confirms to me that a logistic model, which is this p times m minus p, is a very good choice for the ultimate type of model that we want. Now, we're looking for the value of k, and if you think about it, here are the p times 14.3 minus p values, and here are the delta p values. K is simply going to be the slope of this line, so now I'd want to do a visual estimate of the slope of this line, or possibly some other options. So I think if I click on one of the data points and right-click and add trend line. We'll talk about adding trend lines and various kinds of interpolation much more later. For the moment, I'm just going to jump ahead and have Excel do a linear fit and display the equation on the chart. And when we do that, I see a value for a slope of about, let's move this a bit, value for the slope of about 0.0395. And so that is apparently a very good fit line, and that information is what we were looking for regarding the value of k, 0.0395. So from linearized graph, k is approximately 0.0395, and then our model will turn out to be delta Pn equals 0.0395 times Pn times 14.3 minus Pn. That's the difference equation. And our initial population P0 is actually given in the table to be 1.28. There's our mathematical model. Okay, that settles the first question. The second question says, test the fixed points of your model for stability. So remember, right here is our f of p function. And so for part 2, that's where I want to begin. With a f of p equals 0.0395 times p times 14.3 minus p. And what we're supposed to do, if you remember the theory, is take a derivative. Might be, oh, hang on just a second, conceptual mistake on my part. Maybe you caught it, maybe you didn't. Not quite. On the left-hand side here is delta Pn. That's Pn plus 1 minus Pn. Let's go ahead and write that out. So I know that Pn plus 1 minus Pn equals 0.0395 Pn times 14.3 minus Pn. But our f that actually should be used is the right-hand side when the left-hand side is just Pn plus 1. So if I go ahead and solve for Pn plus 1, I get, let's move to this Pn to the right-hand side, Pn plus 0.0395 Pn times 14.3 minus Pn. Important step here. So now f of p is p plus this other term. Okay, so now we're ready to go ahead and take a derivative. So first term is 1, and I'm trying to do this in my head. The 0.395 is a multiplying constant. And then when I take the derivative, there would be a 14.3p term, which has derivative 14.3. And there would be a minus p squared term, which has derivative minus 2p. The next thing evaluate the stability of the fixed point 0 is to plug in p equals 0. And we would get 1 plus 0.0395 times 14.3. And I don't care what the number is. Remember only that whether it's greater than 1 or less than 1, this is clearly greater. And that tells me that p bar equals 0 is unstable. Whereas the other fixed point, f prime of 14.3, gives me 1 plus 0.0395 times 14.3 minus 2 times 14.3 is a negative 14.3. And this quantity is certainly less than 1. In fact, if you work it out, it's about 0.4-ish, something like that. I do need to talk about the magnitude here, so I was worried a little bit about whether I would go below -1 in magnitude. I don't. This is about the correct number, and so p bar equals 14.3 is stable. Theory agrees with what I already suspected, or at least hoped. 14.3 is indeed to be a carrying capacity, and so if we start with a population less than that, like 8 for example, I would expect the population to go up, approach 14.3 and linger there. On the other hand, if I started with an overpopulation, something like 18 or something, I would expect that to cause population decline down to 14.3. So if you deviate from 14.3 a little bit, you should come back. On the other hand, down here at 0, as long as I even have one pair of deer, they start the reproduction process, the population will grow up toward the carrying capacity. So in particular, I'm moving away from 0. 0 is an unstable fixed point. The third thing that we were asked to do is to graph the predictions of our model. So let's go back to Excel. And I have the 0.0395 number that I'll need. Let's go ahead and get rid of this graph now. And let's make a column for the predicted populations. So we're starting out here at 1.28, and we get successive populations as follows. Each population is the previous one plus my 0.0395 times the previous population times 14.3 minus 14.3 minus the previous population, like this. And if I take that formula and drag down, we get here. So now the second column, column B, has the actual populations. The fifth column, column E, has the model's predicted populations. Question: how accurately do the predicted agree with the actual populations? So let's go back and generate a scatter plot of these, and this quantity, let's see, that wasn't quite what I wanted to do. I'm on Office 2010. If you're on 2013, things will look a little differently. Let's see, let's add well, let me go on. If I can figure out at the end how to add titles, I'll come back. I want to add a set of data to this. So let's go ahead, and I clicked on a data point, selected data. Let's add another set of data to this. This will be the predicted, and the x values are going to come from here, and the y values are going to come from here. And we'll go ahead and add those, and that should be enough. Okay, you have to look really close to see this now. I'm going to enlarge a little bit. I had blue diamonds for my original data. That was the actual population. Now I have red squares for the model's predicted population. And it's like, where did the blue diamonds go? Well, the red squares overlay them almost exactly. Now out here, here, you can start to see the blue diamonds poking above. In other words, the model is actually underestimating the population just slightly here through this region of rapid growth. But overall, a remarkably good fit. If we could do this well in math modeling, if we could always do this well in math modeling, we'd be a very happy person indeed. This is a remarkably successful model for this particular population. Okay, the other model that I would like to look at is an example of a dynamical system, which just means that we have more than one difference equation involved. And this is an example of a very popular problem in ecology and in math modeling called a predator-prey model. So, as you probably know, fox unfortunately eat rabbits. It's sad to think, but it's true. And so the fox become the predator, the rabbits become the prey. Meanwhile, each species is trying to reproduce and increase its population in its own right, and because the rabbits are contributing to the success of the fox and the fox are contributing to the demise of the rabbits, there is interaction between the two. So we need the rabbit population to help describe the fox and vice versa. Here is a proposed model for this system, a very simple one, about the simplest one that you could obtain or use. Let's look at this for a moment. The next year's population of the fox is 0.3 times this year's population of the fox. This is just natural reproduction. You need fox to get fox, and 0.3 is some sort of baseline birth rate. But fox reproduce more rapidly when there's a good food supply. The animals are more likely to have time to breed and raise young. The females are more likely to be fertile and so on. And so here is a term that says you'll get more fox if you actually have more rabbits around to be the food supply. Regarding the rabbit population, let's come back here for a moment. This number A is going to be a parameter in this model, parameter of interest. It's going to represent something that I, the ecologist, maybe I'm managing a national park or something, I, the ecologist, have some control over. This is a very persistent thing, but we don't show that again. So perhaps I can control the vegetation, or maybe I have control over some boundary fence where I can actually let external animals in or internal animals out or something. Anyway, I have some sort of control over this number, and we'll investigate what happens as we vary it. The rabbit population, here's a negative term. A is going to be a positive number. So this says if you have a lot of fox, they'll tend to decrease the rabbit population. That's the munch-munch effect. And here is a positive term. If you have rabbits, you'll get more rabbits. Notice that the birth rate for the rabbits is much higher than the birth rate for the fox. That's reasonable and certainly what we're going to do in this model. Suppose we have initial populations of 2 and 10,000 fox and rabbit respectively, and we're interested in seeing what happens as we vary A. So in particular, we're interested in the long-term behavior of this model. That's very common in dynamical systems. We might care slightly about what happens over the next year or two, or time period or two. But our real interest is what happens in the long run. Let's do an Excel simulation here. So I'm going to have a column for the fox population and for the rabbit population. And I'm going to have this parameter A that I'm adjusting, so I'm going to make a named cell for that parameter right now here in D2. And here we go with plugging in the fox and rabbit populations. I initially start with 2,000 fox and 10,000 rabbits, and thereafter the fox population goes as, so here's a formula, the next year's fox population is 0.3 times previous year's population plus 0.5 times previous year's rabbit population. As far as the rabbit population, the next year is minus the named cell A times previous year's fox population plus 1.5 times previous year's rabbit population. Let's take these formulas and drag them down for 25 years or so. And then I can adjust the value of the parameter A, first of all to be 0.64, which was the first value requested from the worksheet. And finally, let's do a graph. And I realize now that I didn't make space for my time values, so we'll insert a column here, and this is month. And let's start with 0 and fill this 0 here. Down fill series. Okay, now I want both of these populations on the same graph. Let's highlight this whole region and insert a scatter plot. And series 1 is the fox population in blue. Series 2 is the rabbit population in red. I thought I could rename these. I don't seem to be able to edit. Okay, so we'll just remember fox are in red, rabbit are in blue. With this scenario, clearly both populations seem to be exploding in time. So if I come back here, what we see is uncontrolled growth. The next value of A was 0.715. Let's go back and put that in. And what we see here is an interesting situation. The populations both increase for the moment, and then they start to come back down again. If you look very carefully, remember the rabbits are red, the fox are blue. If you look very closely, you see that the rabbit population peaks just very slightly before the fox population. What's going on here biologically is the rabbit population starts to increase, the foxes say, hey great, lots of food, and so they increase too. But eventually the fox eats so many rabbits that the rabbits say, wait a minute, I'm peaking here and now my population is starting to get eaten. But as soon as the rabbit population starts to go down, the fox population has to follow because the food supply is decreasing. A little foolish on the part of the foxes to sort of eat their seed. So let's actually continue this. It's not clear to me yet whether this is going to go down forever and go extinct or whether it might recover. So let's actually continue this for some more time. Yeah, to 100 months or so, and we'll keep dragging this population down. Let's get rid of this graph and generate another one with more data. Scatter plot. Okay, this is pretty convincing that there's this initial spike in both populations, then I'm going to see population decline and both will go extinct. Extinction after a brief population spike. Let's go ahead and try a equals 2.5. Well, if I think about what this a is, in some sense it's a hunting efficiency. The higher a is, the more the fox population will tend to decrease the rabbit population. So if already at 0.715 the rabbits are going extinct, then surely at 2.5 the rabbits are in trouble and therefore the fox are in trouble as well. But let's go ahead and check it out. With a equals 2.5. So on the table of values, I very quickly see the rabbit population going extinct and then the fox population within the next year or two. If I go down to the graph, I'm hoping to see something rather interesting. Notice my numbers are getting gigantic and the graph is not really able to display very much. So this time let me go back and trim some of these later values, or better, I don't even need to cut them. Let's just generate a new graph with part of the data. I guess I had it highlighted, so I thought it knew what I wanted. I should re-highlight part of the data. Let's pick up the first 40 years or so. And that's still too much. I'm not seeing what I wanted to see for the first few years. How about the first 25 years? Okay, what you start to see if you look closely is some oscillation. So both populations going up, then both going down, then both going up, then both going down, then both going up. And this is actually going to continue with wilder and wilder oscillations. This is physically or biologically meaningless. The populations have gone extinct long ago. But mathematically, this is an interesting phenomenon of oscillatory behavior. If negative populations were meaningful, it's like there's a very complicated interaction going on here. And furthermore, you notice that things don't necessarily seem to be quite in step as much as they were before. So my point here is we're starting to illustrate some behavior that might be considered chaotic or very unpredictable mathematically. This is a very simple system. If we get more complicated systems, we can certainly start saying more interesting mathematical behavior, which may or may not be biologically realistic. Finally, so this was extinction. But mathematically interesting oscillations. And the final question was, what about the possibility of a fixed point? So now notice that there are two populations involved, and so a fixed point needs to be an ordered pair. If I start with a certain value for the fox and a certain, possibly different value for the rabbits, will both of those two populations stay constant? So here it seems clear that I'm badly that the fox are badly overeating the rabbits. Let's go back down to 0.6 or something like that, where we had more reasonable numbers. And it seems like this is a uncontrolled growth situation. How about we try 0.65 and still growing, but less so. If I try 0.7, that seems pretty promising. I'm going up and leveling off. Maybe 0.71, which is very close to one of the values that we took. And okay, that seems to be peaking and going back down. So actually 0.7 seems to be about as close as I can get. And that turns out actually to be what it is. If you come back here and solve a system that says f bar equals 0.3 f bar plus 0.5 r bar, and r bar equals minus 0.7 f bar plus 1.5 r bar, you will actually find out that this system has a solution to the 210 that we found. Or in fact, I believe any multiple of that. I should have worked ahead a little bit to probe the math a little bit. But this example illustrates that a dynamical system, two equations or more than two difference equations, can actually have a fixed point as well. And from an ecology viewpoint, this is interesting. Two populations interacting have somehow settled on a position or a situation where they coexist. Neither one goes extinct. And that's what I wanted to say about the second model. Thanks.